I believe I have figured out how I can use screen capture on the iPad to record instead of using Explain Everything, which then, if I can do screen capture, allows me to use the Notability app, which I'm more familiar with and I like better. So here we go. Hopefully this works. To finish up the lesson from yesterday, the section 5.5 notes, we had just a little bit of applications left. So I'm going to try to roll through this as quickly as I can, save you all some time. Hopefully you find this interesting. I certainly do, especially right now, and I'll explain why here in just a moment. The applications we're talking about are applications of exponential functions. And the first formula here is one that you're familiar with. You have seen this formula, the formula for compound interest, many times at this point throughout probably Algebra 1, Algebra 2, and pre-calculus. The formula breaks down in this way, where P is what we call the principal investment. It's the initial amount of money put into an account. R is, of course, the interest rate, usually as a decimal. Not usually, it must be as a decimal, so make sure it's not a percentage. And then N represents the number of compounding periods. Number of compound periods. And so in this formula, we would calculate the amount of money that is in an account at any given time based on, well, actually, I guess this would be after 1 year. It's not any given time. In order to say any given time, we would have to take this formula and multiply by t up here in the numerator. And now this formula is looking really wonky with all these things that I've written on there. But I'll write it again. It essentially looks like this. A equals the initial principal times the quantity, 1 plus the interest rate as a decimal divided by the number of compounding periods, all raised to the number of compounding periods times the amount of years. That formula represents the amount of money in an account at any given time t. Of course, t measured in years. So if it's a partial year, then t would just be a fraction. And this is a standard compounding interest formula or compounding formula that tells you the exact amount of money, which includes the initial principal plus the interest. I could sit here and go through a derivation of this formula. I may have already done it. I can't remember in class earlier this year, but it is an extremely important formula for basic compound interest. What we're going to discuss is what happens to this formula if we let the number of compounding periods n approach infinity. If n approaches infinity, what happens to this formula is really pretty interesting. And in order to see what happens, we're going to analyze both the theorem that you see here at the bottom, theorem 5.15, that's, of course, this theorem, and the table here right above. So let's take a look at the theorem. Basically, the theorem says that if you take the limit as x approaches infinity of 1 plus 1 over x to the x power, then through a little bit of simple algebra, you could rewrite the expression inside the parentheses. You could rewrite this expression as x plus 1 over x. And then as x approaches infinity, this limit actually turns into e. And that's where we are going to back up and take a look at this table. The expression x plus 1 over x, all raised to the x power, if x gets increasingly larger, this table is kind of showing us what happens. If x is 10, if x is 100, all the way up to x equal 1,000,000. If x gets increasingly larger, then the value of that function, x plus 1 over x, all raised to the x power, gets closer and closer to the number e. And so just by looking at a table, it's easy to hypothesize that the limit of this function equals e. Now, that's not exactly a formal proof. As it says here below, the proof of this is found in the back of the textbook. in Appendix A in the back of the text, which I don't think any of you have a hard copy of that text, but it's not exactly a proof, but it's pretty convincing. If you look at this table, that if x gets increasingly larger, then that function is approaching the value of e. Well, how does that fit our compound interest formula? Well, you've probably heard it said that if n approaches infinity in this general basic compound interest formula here, if n approaches infinity, then this formula turns into PERT. Turns into A equals P times E to the RT. So what we're about to do is we're just going to use this expression and this limit to show why the formula turns into PERT. All right, so if I scroll down just a little bit, there's a bit of a proof down here at the bottom. Let me move this PERT down. Now, of course, the first thing to recognize is that they are allowing, in this formula, they're allowing t to be just 1. So t is not present in our proof. You could say it's multiplied by 1 here if you want. T is not present. So kind of ignore that. Just consider the t hanging out off to the side if you want. But let's take a look. Our expression, the original expression from above, highlighted there in the red, is what is inside the limit here. So we're looking at this and compare it to what's highlighted in red. One of the negatives about this is maybe I do have a pointer. Oh, they've added a pointer. Fantastic. Way to go, Notability. Anyway, I get excited about this stupid stuff. So you can see here that this expression is the same as this minus the t value. If I get a little creative with it and I say let's go off to the side, let's let let's say n over r we're going to call x. All right, that's actually said down here. And let's transform this expression here. Whoops, that's a little bit too big of a highlighter. Let's transform this expression r over n. Technically, if you think about it, r over n is equal to 1 divided by n over r. Right? If I have this is basically saying the reciprocal of n over r, and so the reciprocal of n over r is r over n. So they're rewriting this expression in this way first, and notice they got a little creative with the exponent also. Here that I've highlighted in blue. Let me zoom in just a little more. Here I've highlighted in blue n over r raised to the r power. When you raise a power to a power, you multiply. And so if you multiply n over r times r, you're going to get n, which takes you right back to where it was to begin with. So they got a little creative and they're rewriting it. Then if we say that n over r, that n over r is in fact equal to x, well then we can replace the 1 over n over r with 1 over x. And then we can replace the n over r in the exponent with x. Then we see very clearly that this limit here matches the limit up here. All right? They did a little variable replacement. I just explained all those replacements. If you didn't quite get it, you can go back and watch the video again if you want. But I love this proof. I really do. It's a very fascinating proof to show that if the number of compounding periods approaches infinity, then this limit turns into e. And so we get from our original, I'll rewrite it again so I don't have to keep scrolling, a equals p times 1 plus r over n to the n power. We get well, nt power technically, we get from that to PERT, if the number of compounding periods approaches infinity, or, as they say, if the number of compounding periods is continuous. If interest is compounded, if interest is added or combined with the amount of money in the account every fraction of a second, then we look at the formula. We turn the formula into PERT instead of this formula up here, the compound interest formula. If I take this formula and I just throw t onto it, it's just going to hang on for the ride the whole time. And you can see that we end up with officially p times e to the rt. All right. So there you have it. The compound interest formula, if the number of compounding periods approaches infinity, is technically going to turn into base E. All right. One thing I did leave out here in the discussion was this p value. Notice that all they did was move the p out in front because that is the initial principal, and the initial principal is a constant. So it moves out in front and it hangs along for the ride throughout the whole problem. All right. So that shouldn't be too complicated to understand. That just move out in front. All right. So our two formulas, all that said and done, you're not going to have to ever memorize this proof. You're not going to have to show the proof in any way. I just showed it to you because I think it's pretty fascinating. But there it is. Ultimately, all you need to be able to do is memorize and know this here, and I think you do. Most students by this point are familiar enough with compound interest that these formulas are not too hard. All right. So summary of compound interest formulas: you got to know the original version for n compounding periods, and you have to know the continuous one, which most people do, PERT. All right. We're going to use it. Let's move on. Example 6 says, if you deposit $2,500 into an account that pays an annual interest of 5%, 5% is technically R equal to 0.05. Find a balance in the account at the end of 5 years when the interest is compounded either quarterly, monthly, or continuously. So 3 separate problems. This is basically plug and chug. If it's quarterly, then quarterly equals 4. And our formula becomes A equals 2,500 times 100%, 1, plus the interest rate, 0.05, divided by the number of compounding periods, 4, all raised to the number of compounding periods times the number of years. The number of years was 5. And that comes out to approximately, I've got the calculator already worked here, approximately $3,205.09. All right. In B, if we're doing it monthly, then n is 12. The number of compounding periods, the amount is 2,500 again, times 100% plus the interest rate 0.05 divided by 12, all raised to the 12 times every 5 years. 12 times a year for 5 years. And that number comes out to, we're compounding interest more frequently, so there should be some more money, and it is just a little bit more, $3,208.40 when you round. All right, and then finally, if we allow the number of compounding periods to approach infinity, that's continuous. So n approaches infinity. That gives us the PERT formula. So the amount of money in the account is the original $2,500 times e to the interest rate 0.05 times 5 years, and that comes out to $3,210.06. All right, not a whole lot more, but a little bit more. Now, in the real world, if you were looking at accounts like this and you said, well, that's just stupid, why would anybody go for a 4 times compounded or 12 times compounded when clearly an infinite compounding is going to get you more money? That means, again, they're adding interest on the interest more frequently. Obviously, if you had these 3 choices, you would go with the infinite compounding. The problem is that infinite compounding, or continuous compounding they call it, gives you a low interest rate in most cases. You don't get the same interest rate. So the interest rate might be smaller than 5%. In fact, 5% is a pretty excessive interest rate. Most accounts do not yield 5%. My wife and I have a high yield they call it, savings account, and I think the rate is like 0.08%. I mean, it's outrageous. All right, so there you have it. Those are the three answers. It's plug and chug, calculator problems, and they aren't even really calculus at this point. All right. Really fascinating for this point in time is number 7, logistic growth. I should note the solution to the logistic growth model is a differential equation. That is something that would have been one of the last things we would learn in the entire course, but it has since been cut out of the course due to coronavirus and schools being shut down. So, but I am going to make you look at this example because it's fascinating, number one, and it does show what is going on right now with coronavirus stuff. A bacteria culture is growing according to logistic growth function, and they don't explain this function, they just give you a function. If you weren't told it was logistic growth, you probably wouldn't know that it was a logistic growth function. And that makes sense. Not everybody memorizes that. Please note this little thing right here is a comma. All right. So be aware. This is just a little comma in the formula. Anyway, 1.25 divided by 1 plus 0.25 e to the negative 0.4 times t, where t is some time greater than or equal to 0. All right. It says y is the weight of the culture, in grams. T is the time measured in hours. It says find the weight of the culture after 0 hours, after 1 hour, after 10 hours, and then the real fascinating question is, what is the limit as t approaches infinity? All right, well, this is just a plug and chug. They gave you the formula. You didn't have to find the formula. You didn't have to do any work. Finding the formula would have been, like I said, a differential equations problem. They would have given us some other information to start with. We would have had to solve, and we would have ended up finding in our solution this original formula. We'd find y. Then we would have to use y to answer these questions. We don't have to do that now. So they gave us the formula. We're just plugging in. So you'll notice that each of these, I've already done it, or I just posted them from the book because they were plug and chug problems. If you let t be 0 hours has passed, then you see that you get 1 gram. Just plug that directly into the calculator, you end up with 1. If t is 1, you end up with 1.07 grams. If t is 10, you end up with 1.244 grams. All right. These values are modeled on the logistic growth function. And that's the part that is really quite relative right now in this point in time. If you have looked at any models about the coronavirus spread, especially as it pertains to what's gone on in China, then you have seen that the spread in China has flattened, and everybody's talking about flattening the curve. Logistic growth is, in a word, logical. Nothing ever grows exponentially forever. That would be an exponential growth model. That is technically not realistic in any scenario. At some point, some parameters, something is going to slow down the growth. And that is what happened in Wuhan. They found a way, or at least as far as we're told, they found a way to slow down the model, and it grew exponentially, and then it hit an inflection point, and that growth started to slow. And eventually it leveled, and they are looking at a model that looks like the purple curve instead of the red curve. Very much right now, the USA growth, the Italy growth are still in this red curve, and we have not hit the inflection point that has turned that growth to a more negative or slowing down the growth, at least not negative, but concave down as the inflection point would yield. We haven't hit it yet in the U.S. We haven't hit it yet really in any other country except for South Korea and in China. But logistic growth has happened, and that's what we're reaching for in our flattening the curve statements that you keep hearing all over the place. So that brings us to D. What is the limit as t approaches infinity? If you let t get infinitely large, look where I'm pointing down here in this in this part D explanation down here. If t gets infinitely large, then this expression here is, because it's got a negative exponent, it's technically 1 over e to the positive 0.4 times t, where t is infinitely large. That's going to approach 0 as t approaches infinity, because 1 over infinity, 1 over e to the 0.4 times infinity is 1 over infinity. 1 over infinity is 0. And therefore, it's 0 times 0.25, and that's where you get this 0 from. And so you're left with 1.25 over 1, which is 1.25 grams. What is that saying? That is saying that as time gets infinitely larger, as time passes, if enough time passes, the maximum value you're going to have of this bacteria is 1.25 grams in weight. It's going to start at 1, apparently, and it's going to go to, or it's going to start at 1 because at time t we had 1 gram, and it's going to max out at 1.25. In Wuhan, they started with however many cases, presumably 1 case initially, of coronavirus, and eventually they maxed out at about 80,000. In China it was 81,500 is where they are now. But it's still growing very, very slowly, but it's been level at about 80,000 for the past over a week now. So they have hit this part of the curve, and it's really an interesting thing. So interesting that I'm actually going to have you look at a website. I don't know if I can copy the website on here, but I did have it brought up here. Not a website, a video, I'm sorry. I'm not going to make you watch this whole video,
growth is familiar to most
I'm going to copy it and say,
yet human intuition.
I strongly recommend you do. So let me copy that and see if I can just post it, and then maybe you can. Yeah, there it goes. Maybe you can type it in or somehow copy that and then watch that video. It's awesome. A really good video about the growth of the virus. It was put out just a few days ago, March 8th, I think, so a little over a week and a half ago, I guess. Watch that video on the Wuhan spread. It's only about 7.5, 8 minutes long. Very, very, very good video, worth your time. All right, I'm going to stop there. Stop wasting your time. Y'all, good luck with this. It should be simple problems in the WebAssign, and we'll see you tomorrow.